Welcome to week 2 of COM 226 Hardware, Software, and Cloud Computing with Professor Marc-André Léger. So, just to keep in mind what we've been talking about so far, and bring this back to our reference model from the beginning of the course, from the general introduction to how strategy connects to technology. Justifying why we're talking about business technology and not computers. We started with our value proposition. It led us eventually to our strategy. This allowed us to talk about what's the building blocks that we need in our value chain, and then based on these building blocks, what is the supporting technology that is going to allow us to do the work that we're looking to do. So, and that's where we got talking last week about information technology and information systems. And so, if you remember when we were talking about information systems and technology, we mentioned that systems have multiple components. And so some of these components that we're going to be talking about today, and we are also going to be using some different models. And talking about information systems, we're really going to look to two models. So this first one, where we're looking at information systems to be composed of hardware, software, databases, network, and people. So that's one of our models that we're going to be using to explain what is an information system. And at the middle of this, what we see are the business processes, where we have an IPO process, input, processing, output, with a feedback loop telling us, how we can improve the business process. So the business process, the IPO, that's what the software is going to be doing. The hardware is going to be running the software, the database, the data, and being used by people, and talking to different components through the people, through the hardware, at the network level. So this is one of our reference models, keeping in mind the very important notion of system. So a system is a group of different things working together towards a common purpose, a common task. And in information system, this task relates to the processing of information. So we're looking at things that will allow us to be more efficient in managing information. And so that's what this model here is all about. Another different information systems is going to be using, instead of the model that I just showed you, to me using a model that includes 5 components. So we'll be talking about what are the 5 components of an information system, being the hardware, so that's the equipment, and all of the hardware, so not just the computer, but also all the peripherals, so like things like printers and other monitors, input devices like a mouse, like a keyboard, or output devices, so like your monitor or a printer, and sometimes hybrid devices that are both input and output. So, for example, if you have a printer, but that's also a scanner, so it's an input device, the scanner, but it's an output device, the printer. So that's sort of a hybrid device. I do want you to keep in mind, and particularly, for the final exam, there's usually you're going to find questions about different devices being input or output devices. So think of, does this device allow us to get information into the system? That's input. Or does it allow us to retrieve information from the system? So that's output. So like a monitor, a printer, our output devices, a keyboard, a mouse, a scanner, These are all input devices. So that's all of these input and output devices are including the computers themselves. These are all part of this category of hardware. The software is what makes the computer work, right? Because hardware by itself really does nothing. A computer with no software is a boat anchor, really, or a paperweight. So it really is useful because there's software that makes it into something useful. And this something useful has something to do with helping us do our job, which leads us to the next element, the next component, which is the business process. So the business process is being what we do. And so one of the things the software is going to do is going to be to help us with these business processes. And then in doing these business processes, we need information. And so for us here, the information is the data. The raw data is the base of information, if you remember from what we talked about before in last week's class, when we talked about the value of information, the structuring of information, but at its raw form, which is what is actually stored inside of the software, inside of the hardware, which is being used by the software, that's the actual data itself. And when we get it organized, it becomes information. And when we get it really structured, it becomes knowledge. So, but it's what we need for the business processes and the software. It's the data. And then finally, there's people. People are an important component of an information system, like the users that are actually using the system, who create the value that is being generated. So all of this has to do with users, with people, keeping in mind that people are vulnerable, so that people make errors, people cause risks, people are, can potentially steal from us, but I mean, not obviously not all your users are going to be stealing from you, but there's always this potential, there's always this uncertainty associated with people. Whereas software, if you know the software is running properly, if you've taken out all the problems out of the software, then it's going to keep doing the same thing every time. However, people are not as reliable, but we can't really get rid of them. People are, humanity is based on people, right? So, I mean, our employees are going to be people, our customers are going to be people, our users, people accessing or connecting to our system are going to be people. So again, here I want you to keep in mind that we're really talking about two different models, two different ways. So the first one from the previous slide and these components. So very often when we'll be talking about an information system, we'll be referring to one of these two models. Probably in my course, in my class, more to this second one, where we'll be talking about what are the different components. So looking at these components, let's start with talking about the equipment, the hardware. And we need to look at a little bit about the history of computers, how long have they been around, etc. For this purpose, what I've done is I've added some links on Moodle to some other videos that go more into detail of this and that are from very reliable, trustable sources on this. So we don't spend too much time here with a long 2-hour course on the history of computers. But I do want you to keep in mind to try to understand when computers were invented, which is really an unanswerable question. Because it really depends on what is your definition of a computer. If you look at an old, like pre-1945 English language dictionary, you're going to find the definition of a computer as being a person. If you've ever saw, I forget what these, Hidden Figures, the movie about the African-American women who worked at NASA and who were doing calculations for NASA, their job title was computer. So really a computer, for a very long time was defined as a person who did calculations, who did computations for all kinds of reasons. to do log tables or ballistic tables or all kinds of different things. And then when we talk also, when we're thinking about a computer, for most of us, when we think about computers, we're thinking about electronic devices. But really, a lot of computers that existed, early computers were mechanical devices. So we, go back a few thousand years. They were devices that were developed in ancient Greece that were used to calculate the tides or lunar cycles. If we look to the golden age of Islam, about 10th, 11th century, we know there were devices that were used to calculate prayer time, or based on the stars to calculate the direction towards Mecca for prayer. And these could definitely be defined as mechanical computers. And really, a lot of the technology that we use today when we're talking about computers, binary systems, and things like that, were all things that were developed by the Muslim scholars of that period. Algorithms is really an Arabic word, right? So it's really hard to say when computers were invented. Now, for us, and when you watch some of the videos I've linked to, you're really going to be talking about electronic computers. There were some early steam machines that were developed by a guy called Charles Babbage around the mid 19th century in England. And those were the first programmable devices. So these early mechanical devices that I was talking about really had a single function, and they were built for that function. Babbage's analytical machine could be programmed, and there's actually the world's first programmer was a woman called Ada Lovelace, who was a countess. She was the daughter, I believe, of Lord Byron, and she actually wrote the first book on how to program a computer. And when we look at more recent people like Alan Turing, I'm sure you'll hear a lot about if you look into the history of computing. But he's the guy that you see in some of the movies who's decoding the German Enigma machine in the Imitation Game movie from a few years ago. So this guy, Alan Turing, he actually knew of the work of Ada Lovelace, and a lot of his early work was based on things that had started with Ada Lovelace and Charles Babbage's machine. So, but really, the early electronic computers have to do with the vacuum tube. So, Lee de Forest around 1906, I think, and then started to be used by some researchers in universities around the time of World War One, but really emerged after the war, after the First World War, and up until World War II, where the Germans Konrad Zuse built some calculation machines that were used by the Germans. And then, of course, the Americans with the Enigma, the decoding thing that we see in the UK with the British with Alan Turing, and the Americans with ENIAC that was used in the Manhattan Project and also for ballistic calculations around World War II. So, and that's really when we start thinking about, the invention of the computer. But really, it's about the invention of the electronic computer. Us, like when I say us, I mean like normal people or businesses, only started using computers much later. The first business uses of computers happened in the 1950s with the UNIVAC being developed. So that's a vacuum tube and then, a transistor based. And that's what the illustration that we're showing here is that of a transistor. Were really the first, when computers started to be more usable, more reliable, and more affordable relatively. It's around the 1950s. And it's about that time where the first computer languages started to emerge as well. So, because before that, you really had to be an engineer or a scientist to be able to program a computer. But with the introduction of computer languages, you could teach someone, just like you could teach someone a language, you could teach someone how to talk to a computer, how to program a computer, and how to write software without having to hardwire it into the machine. And so that's really when the mid 50s to late 50s, the first business uses of computers. And then the late 60s, early 70s, with the introduction of the microprocessor, microcomputers, or what we refer to as personal computers, PCs. And of course, with the arrival of PCs, then computers became a lot less expensive, a lot more reliable, had less heat problems, etc. So I mean, being a lot smaller as well. Early computers, like around World War II, would fill the equivalent of a full floor of a building. By 1960, they would be the size of a large refrigerator, and by the 1970s, mid 70s, they were the size of a suitcase or a briefcase. And today, as you know, the computers can be relatively small, so small that it would fit inside of your pocket. Your phone is actually a very powerful computer. And that's all because of the microprocessors. Evolution from the early standalone machines to then these large machines, but that had terminals so that many people could use them at the same time. And those terminals weren't really very smart. They were just like a keyboard and a screen, or even in some cases, just like a typewriter. And this is how you could communicate. So here we're looking at, when I was talking about sort of UNIVAC and that era, so 1950s and 60s, these started to arrive. And dumb terminals were actually around for a very long time. They were around when I started working in IT in the early 80s. We still have a lot of these dumb terminals being used with these mainframes. Although today you don't really see them anymore very much. But they do still exist, but pretty rare now. Perhaps only for backup purposes. Because now, of course, in lieu of terminals, we use computers as a terminal, as a way to connect to these large mainframes running in the background. So you'd still see mainframes being used in banks and large financial institutions, in the government as well. You'd find some uses for mainframes. But most of us, what we're using are personal computers. And so when personal computers arrived, again, if you watch the different videos about the history of computers, you saw with Intel introducing the Intel microprocessors in the late 60s, early 70s, and then being adopted by different vendors, think companies like Apple, Hewlett Packard, and many others. But these early personal computers were standalone. They were just working on their own. Perhaps had a printer connected to them. But a little bit later on, so local area network. So connecting all these computers together. Early networks in the 1960s connecting mainframes together, and around the late 80s connecting personal computers together. And so that now the computers could share different services, and they could share different peripherals. They can share more expensive hardware. Again, I'll suggest that something that you might get more information about by looking at some of the videos that are available. Certainly, if that's something that interests you, or if you're doing your major in business technology, then that's something that you're going to need to learn a lot more about. But for most of you business students, just understanding that we have all these different personal computers, but now we started late 80s, early 90s, we started connecting them all together so that they could exchange information. And also, some more sophisticated machines could act as a server, doing some of the work. The more labor intensive or calculation intensive work could be done on these servers, as well as managing very large amounts of data we can do on these servers. So these bigger, more complex, more powerful personal computers were now serving other machines on the network, other personal computers who didn't need to be as powerful, or who could focus on doing other on doing other things like handling the display or the graphical user interface. So that's when we saw this client server type of model. And then as these grew and became more and more sophisticated, then we started to have the whole business, the whole organization connected. That's when we started to see enterprise computing. And then finally, more recently, we've been offloading some of the processing or some of the services or some of the work out on the internet somewhere to service providers or to third parties. And because it's out on the internet, we refer to it as the cloud. So that's where we are. A lot of services now, if you use things like Dropbox or cloud iCloud on the Mac or the Office 360, Office 365, or all of these different type of OneDrive and things that require you to be connected to the internet so that they work. That's the cloud computing. And of course, mobile computing, particularly these days with everything that's going on in the world, we're really in an environment where we're mobile. Also, in certain parts of the world where it's just not really feasible to set up telecommunication infrastructures with wires, a lot of things are happening via mobility. So through cell phones, for example, or things like 5G that we're hearing a lot about, and that's becoming more and more prevalent. 5G is very, very high speed networks, but that don't require the same physical structure to the client, but that can be done using, radio frequencies. So just like your cell phone, but imagine your cell phone with a super high bandwidth. So you can do more than just use the phone or do video conferencing or things that you're normally doing or browsing the web from your phone. You could actually have, all the services of a business through mobility. So that's where pretty much we are today. Important thing to understand for us, for students, is this idea of Moore's law. So this is really a guide that was developed by a guy called Gordon Moore, one of the inventors of the microprocessor, one of the founders of Intel, the company that makes most of the microprocessors that are used in most of the computers that we use today. They're made by Intel, or they're copies of processors that were developed initially by Intel. And so he came up with this sort of graph that illustrates how microprocessors have been evolving. And it's been so reliable that we've really made it into a law to try to understand how processors evolve over time. And it really relates to the fact that the number of transistors keeps increasing over time. So really, the number of transistors on integrated circuits doubles approximately every 2 years. So the other thing as well is the speed of these processors. And then the third component of that is the price. So what you need to know as a student at this point is that computers, or the microprocessors, which is basically the brain of the computer, the microprocessors keep getting smaller and smaller. They keep getting faster and faster, and they keep getting less and less expensive. And over time, every time we thought that we've reached the limit of a technology, something happened that push the limit even further. So, there's only so small that we can go, right? We can only make things so small. I mean, there's some physical limitations, like the size of an atom or the size of an electron. But every time that we've come to that close to that limit, somebody invented something. Like, for example, multi-core. So really combining microprocessors into a single chip. Dual core or quad core or X number of cores. pushing the speed, increasing the speed of the processor, of the electrons or the things happening, the bits and bytes, increasing the bus size, going from 4 bits to 8 bits to 16 to 32 to 64, etc. There's always been something. But what I want to focus to you, and what I want you to remember, is computers keep getting faster and cheaper and smaller all the time. So if you've got a situation, you've got a solution that requires a lot of processing power, maybe today it's not really feasible because it's just going to be too slow. But don't worry about that too much, because in the future, there's going to be faster computers. So things like artificial intelligence, for example, making a computer seem smart, it requires a lot of processing power. But because computers, that's really not going to be a big issue, because we know at a certain point we're going to get to this moment in time where we're going to be able to make computers seem smart so fast that they will reach the equivalent of a human. That moment in time has a name, which has been referred to as the singularity. So there's this guy Kurzweil, this thinker, this scientist, who came up with this idea that at some point in the evolution of computers, and he had imagined when he wrote this up a few years ago that this would happen around 2023. So, that's tomorrow. And as we all know, and this is my usual stupid joke that I make every year, that, what happens when the computers get so smart, and well, that's, the start of Terminator 2 or Terminator 1. Skynet goes live and kills all the people because it figures out that, we're the big problem. But in reality, of course, there's things like, and you can read Isaac Asimov and about the laws of robotics and all that. Well, obviously, a lot of people are concerned that we have to put in place some rules and some principles to help us and guide us along this idea, this implementation of artificial intelligence. But what we know based on history, looking back, is that these computers just keep getting faster and faster and faster. And so this can be, they can be very, very useful tools for us. And hopefully they're not going to kill us. So one model that we are using to try to understand how a computer works was this model developed by Professor von Neumann. So this Neumann, I think it's pronounced actually. That was developed, I think, in like late 40s, early 50s. It's been around for a while. But really, all of the computers, even Babbage's machine from the 19th century, or things that were developed by Alan Turing, or the newest iMac or MacBook Pro that you're going to go buy, still today follows this basic model. So this is a very useful model for us to try to understand, how computers work. So really, keeping in mind, at the middle of the whole thing, we have the CPU, the central processing unit. So this is basically the core of the whole thing, right? That's the microprocessor, basically, that you're going to find the central processing unit. And it has basically two other components inside of it. One to do the math, that's the arithmetic logic unit, the ALU. And one to control, circulation, how things are working, the control unit. If you've ever seen the movie Tron, maybe that's something you can watch, you actually see the control unit managing everything in there and doing all the stuff, right? And that's sort of the basis of this sort of movie. It has to do with this central control unit inside of the CPU, trying to organize how everything is happening. Of course, it's a movie, so there's some other aspects to it, and try to make it more interesting. But basically, that's what it is. And so the CPU it's doing all the work. That's the brain. But in order to do work, it's got to have some instructions. You got to tell it what to do. And those instructions, they're going to be in the memory. And in the memory, we usually have a couple different kinds of memory. We have read-only memory, ROM. We have random access memory, RAM. And that's memory that, so the read-only memory is where the basic instructions are going to be, the things that are going to, make the machine, when you turn it on, know that it's a computer. So some of the basic early software that we'll talk about in a couple minutes, in a few slides. And so that's going to be in read-only memory. So, and then of course there's the random memory. And so when most of us, when we're talking about memory, we're really talking about RAM, random access memory. That's where software and data is going to be found. So when the CPU is doing stuff, it's getting data, it's getting instructions, it's all working with the random access memory. So very often when it starts to run out of RAM because you have too much instruction, too much stuff in there, and it's starting to get completely congested, completely full, it's going to make your computer seem slow. One way that you can make computers work faster or have the impression that your computer is going to be faster is by adding memory. What you're really doing is adding RAM. So when I say I'm going to buy a computer with 8 gigs of RAM, 8 gigs of memory, it's 8 gigs of RAM, or 16 gigs, or 32 gigs, or whatever. That's what we're talking about. And so we get information to the computer with the input devices, and we get information out of the computer with the output devices, and I talked about those before. And some of the information will go from the input devices through the control unit, and it'll put it in memory. But we have another kind of memory, which is permanent memory, and like storage. So like your hard drive, for example. So RAM, one of the characteristics of RAM is that when you turn the computer off, it's completely erased. And so the ROM stays there, but the ROM is pretty small and really has only really super basic stuff. Tell the computer how to access the memory and how to access the input and the output. But you need someplace that you can store information more long term. And so that's the kind of memory is referred to as storage. For most of us, we think of a solid state drive, an SSD, or a hard drive, HD, as being this component, this part of memory. So really, memory is everything. Memory is where everything is located. And memory is sending information to the CPU. And then if it needs to display something, it sends it to the output. Or if it needs to the users or another computer to send it information, it's using input. So input could be, a network connection to another machine, to a server, to another client, etc. The output devices could be your monitor, or it could be sending information to another machine, to another server, to another computer out there. So it doesn't matter if you're looking at an iPhone or some kind of smartphone or the world's largest supercomputer, you could basically use this model to get some understanding of how the machine is working. So this model is a very, very important reference model for us. And so you want to keep this model for computers. So let's talk a little bit about software, right? So as you know, software is what makes the hardware useful. Hardware is nice, and hardware is what we see, but what we're using is the software. So at the core, we have the hardware, all the different components of hardware that we've been talking about. But on top of that, we're going to have the software. And so the software is what's going to make the computer work. And we're really going to find two kinds of software: the system software and the application software. So when we're talking about the system software, for most of us, what we're thinking about is the operating system, the OS. So if you're on a Windows or a PC type of machine, Windows is your operating system. And if you're using a Mac OS is your operating system. So Mac OS is operating system, is the OS, right? And so many of our students here at JMSB are using Macs, your Mac OS. That's your system software. That's your operating software. Most organizations use PCs or Windows-based machines because they're less expensive, because also a lot of the business application software that businesses are going to be using, that's running on top of the system software. And there's a lot of application software, specialized software that only runs on a specific operating system. And most of the business software that only runs on a single operating system is really running on Windows. Whereas, there's general application software like word processing, which is Microsoft Word for most of us, or Excel for spreadsheets. This software is running on multiple operating systems like Windows or Mac OS, and most of the Microsoft Office tools or components work on both, but some only work on Windows. So there's Visio that we're going to be using in a few weeks, perhaps some of you will be using for some of the assignments. Visio doesn't work on the Mac OS, only works on Windows. So that's some examples. So the application software is really what most of us really think of when we're thinking of software. But the system software is what's connecting to the machine and what's making the machine work, making it a little bit more, useful. The software are the programs. So it's written in computer languages, which often will refer to as code. So it's coded. And there's computer languages, all kinds, names like Fortran, Pascal, DBase for databases, Oracle, things like C, C++, C Sharp, Java, JavaScript, Python, COBOL, Fortran, Lisp. I mean, all kinds. There's all kinds of different computer languages that are used, and with those computer languages, we write computer programs, which are sequences of instructions in these different languages, and that's what the software is made of. In software, we're going to find documentation, the book, the user guides, things that tell us how to use the software, which most of us never read. So RTFM, read the effing manual, is something that you're going to see a lot when you're an IT guy, an IT person. There's even in some TV shows you're going to see people wearing that as a t-shirt. RTFM, read the manual, because most of the information on how to use the software is there, but the reality is most people just don't read them. System software, that's the operating system. Application software, that's really the functionality, or that's really the software that we're actually using. System software, the operating system, which supervises the operation of the machine itself and how the different things that are going on are going to be scheduled with the machine, and all of the different functions that it's going to be doing. So controlling the activities, the processing, giving you the impression that there's many things happening at the same time. In reality, the computer, the microprocessor, each microprocessor, maybe you have a multi-core machine, so you have multiple processors working at the same time, but each of the processor is doing one thing. And that one thing is happening very, very fast. And so the system software can give a little bit of time, a little bit of slice of a pie to the different things that are going on. And it'll give the impression that you're multitasking, that you're multiprocessing, that the computer is doing many, many different things at the same time. So handling all of that activity, all of these activities, that's a function of the system software. Controlling how you're talking to the peripherals, the printer, the keyboard, the mouse, how it's getting and sending information to those devices, right? Making sure that they work, making sure that we have the pieces of computer code, or what we call drivers, that support these different peripherals. So this, again, is a function of the operating system. It has all kinds of management functions or self-regulatory functions that make sure that things happen in an orderly fashion. It provides as common stuff for all applications to use. So, for example, how the printer works, how the keyboard works, how the monitor works is just done in the operating system. So every time somebody creates a software, they don't have to write specific instructions on how to use the printer. That would be a waste of time. But that's all defined in the operating system. And so if you're writing software, you tell it, talk to the printer, and the operating system knows how to do that part. So it's really, it makes it a lot more efficient rather than having, if you have 5 different softwares with 5 different ways to use the printer, and that would just quickly get into this big chaos. So you get it all managed by the operating system. It's a lot cleaner, a lot more efficient. And then then all of the basic functions of the machine are all going to be handled by this operating system. So as an example of understanding this, how this works, how the system software works, I'm going to talk about how Windows boots. This is an example from a couple years ago, I guess. I haven't updated this slide in a while. I've been using it for a few years, but it really doesn't change much depending on what version of Windows you're using, so it really doesn't matter too much. So if you remember from earlier, I talked about the read-only memory, and that's where you're going to find something called the BIOS, the basic input-output system. So when a computer starts up, the ROM is going to has the BIOS, and the BIOS is going to give the computer the basic information on how to connect to the input and output devices. And you might notice if you're looking at a PC, you might see a little message pop up on the screen saying the BIOS is just being loaded. You might see counting the RAM or counting the memory. If you have a Mac, you'll see a little spinning wheel going on, or perhaps a little bar going. That's the BIOS. And then it starts to load the operating system. So once the operating system is loaded and initialized, that's when the machine can actually start to be useful. So when it's loading the operating system initialization, so that's really the middle line here that you're looking at, it's going to start loading what's known as the kernel. So this is like the core of the operating system. Then it's going to start to initialize the session, so the different parts of it. And then you'll get the Win logon. This is when you're going to get the login screen if you're on the PC. Or, well, really on the Mac as well, you're going to see the little circles with your name or something. And then it'll ask you to connect and to type in your password or to authentify in some way. And so once that is done, then you'll start setting up the Windows and the Explorer, so you'll get like the desktop, and then the computer is going to be ready to go, ready to start working. So that's really how a computer starts up. And again, this is a Windows 7, but it really doesn't matter what version of Windows you're running. Of course, before Windows, when we had other operating systems, it wasn't the same. But starting at about the early 2000s, all of the Windows releases since then have basically been following this model. And for Mac, it's really not that different. So that's the basic computer and the basic way that the system software starts connecting to your machine. So then we get to the application software. So for most of us, this is what we're really going to be using, right? So a spreadsheet like Excel, word processing like Word, desktop publishing software. There's all these different types of application software that we're going to be using. I'm using PowerPoint right now to do this presentation. Graphic software, personal finance, web authoring, communication. I mean, all these different types of software that we're going to be using in the context of a business. Most of us, we use commercial products, so shrink-wrapped package software that we're going to buy. We used to physically buy at a store. Now we just buy it online, buy a license to use software most of the time. There's also open source software, so software for which the original code is available online, and so that you can modify it to your needs. And in many cases, this open source software is also going to be available free, so you don't have to pay a license to a company and you can start using it. So this is something that you are going to perhaps look into, something that you should know about, something that is going to be covered in the book. So I'm not going to go into too much detail. So for most of us in business organizations, we are really not going to be using open source. We're really going to be using commercial packaged software that we're going to buy. And really, the big reason why companies tend to do that is because they can get support, they can get training, and they're just more comfortable with doing that. In reality, there's no reason why companies couldn't use open source, and instead of giving all this money to Microsoft or whoever, that they could develop their expertise in house. But that's really not catching on too much. So there's really not that many companies, at least not in North America. You'll see that a lot more being used if you go to Europe, particularly Germany or Scandinavian countries are going to be relying a lot more on open source. And I personally think it's a pretty good idea, rather than sending your money to Microsoft, developing your own in-country expertise. But businesses make other choices for other reasons, and mostly just because it's a lot easier just to rely on something that you can just buy off the shelf. We're going to be talking a lot about competitive advantage, but one thing is that software, to develop software or to adapt software, can be expensive. If it doesn't really give you a competitive advantage, it's probably more often than that other just easier to just buy something and use it as is. But that's also something we'll be talking about in a couple. Remind you of the value of data, right? As it gets more and more structured, more and more contextualized, we move from data to knowledge, has more and more value. As well as information becomes to knowledge, we move to different types of information systems. We talked, I think last week, about TPS, transaction processing systems. So that's really used by the workers or by the customers. Middle managers will use something called a management information system, or MIS. Senior managers will use decision support systems, or DSS. Executives will use executive information systems and things like dashboards and business intelligence tools to work at a more strategic level. So executives are strategic and they'll be using the EIS. Senior managers and middle managers are more at a tactical level, and so they're worrying about operational stuff, day-to-day operational stuff. Whereas at the strategic level, we're really thinking more about the big picture. And then the workers who are actually doing the work, the actions, what's happening on the front line is done by the workers. So we have different types of application systems, of application software, based on where you are in this continuum between the worker and the most senior executives in your organization, depending on whether you're involved in the day-to-day actions or you're at the more strategic level of the organization. Again, here, something we'll be talking more about in the next few weeks, but you do need to keep that in mind, that we have all these different types of application software, and they really serve a different role and a different purpose in the context. So the last component in today's class is cloud computing, which really has something to do with externalization. So taking out of the organization a lot of the processing power, a lot of the software, the application, a lot of the data, removing it from the organization to the outside. And so really making it more of a commodity rather than as an expense. So here we're going to get on-demand self-service. We're going to use it in a more, or at least the idea is to use it in a more efficient way, to have fault tolerance and redundancy, and make it very easy to scale up or scale down. So think of it like instead of buying your own car, you rent a car when you need one. So if today I need a small car, I'm going to rent a two-seater, a very small electric car. But maybe next week I'm moving and I need to rent a truck. that's what we're talking about, scale up or down as you need, right? In a cloud environment, you're really paying as you go. So you're really dealing with a third party who's providing you the services that you need, and you pay for what you're using. So think of Dropbox, Google Docs. So Google Docs is you're using, a software, right? So platform. No, Google Docs, you're using applications. So applications as a service. Dropbox, you're using storage. So you're using infrastructure as a service. Perhaps you're using Amazon Web Services to run some of your processing or perhaps to do some artificial intelligence. You're using infrastructure as a service. You're using platform as a service. There's all kinds of these different flavors of how you're going to use different services. You're going to externalize some of your services in cloud computing. What's important for you as a future manager to know that it's a really interesting alternative. It's very, very cost efficient. However, it's on the web. It's out there in the cloud. So out on the web, in some cases, you don't really know where it is. So there's a lot of potential security or privacy issues relating to that. In some cases, there's going to be legal issues. There's some stuff that perhaps contractually you can't put out there, or perhaps there's a law like a privacy law. And that's something we'll be talking about again in a few weeks, privacy issues and security issues as well. So that's something that you need to keep in mind. It's not, a single one solution for every problem that you have. But it needs an internet connection. So if for some reason your internet is down, or your phone network is down, or there's been some kind of natural disaster that's causing a problem that you're losing connectivity, you're not going to have access to these services. So that's something that you do need to think about. But, in normal everyday life, particularly for things that require a lot of processing power, but that don't really necessarily create a huge competitive advantage, and there's no special security or privacy issues relating to that, then it's certainly a very, very interesting cost-efficient solution. So it's really a good way to deliver a lot of services. So a lot of organizations today, for things like word processing or email or non-critical apps, if they can go cloud computing, they do it. A lot of companies, web hosting, your web is public anyway. People are accessing your website, your catalogs, your e-commerce site. So that's something that could probably be done really well in cloud computing. Video game companies need a lot of processing power, and it goes up and down depending on how popular your game is. And sometimes it's really hard to figure out in advance, how much power you're going to need and how long people are going to be using this game. So cloud computing is a really interesting solution for these. So again, in the context of this course, there's a few things that you're going to need to keep in mind. Get ready for the final. Things like infrastructure as a service, platform as a service, or software as a service. So do take some time to look at these videos that I've posted, but also to look up in the book and to read up on what these are exactly, because this is something that's having a significant impact on organizations, significant impact on the users, on how we do things. And so some of these, we'll focus perhaps here a little bit on the benefits, the positives. So for the employees, it makes it very easy to access information from everywhere. And we found in some organizations that do rely a lot on the cloud, it was very easy for them to migrate to a new, to a working from home environment in the reality of the recent health crisis that we had to deal with. It's a good way to save money. Do keep in mind that sometimes, saving money is not the only thing you have to think about. If something provides you a very high competitive advantage and there's privacy and security issues, that's maybe saving money shouldn't be your biggest priority in that situation. But generally speaking, cloud, you'll pay as you go. So it's really will save a lot of money because, you don't need to buy as much hardware. And so if you don't need all this software, this hardware, and you don't need to buy the software, you're not going to need as many IT people as well to run it and to make sure that it's working. And you're going to get a company who's going to manage all of this for you. And they're going to manage backups, and they're going to have redundancy, so multiple sites, a lot of equipment, the ability to scale up or down as your needs evolve. So this is a very interesting way to save money for organizations. And then flexibility, I mentioned the scalability issue, certainly, and competitiveness as well, because it allows you to be very, very reactive, to change, to add new services, to upgrade, to evolve very, very, very quickly. Again, I refer to the recent pandemic things. So that gives you a lot of capabilities that can be very, very useful to organizations. And that certainly can contribute to creating a competitive advantage. So that was the lecture for this week. And again, I do want to insist that, to take this course, it's not just watching this video. Watching this video is one way that I found that we could get around some of the issues of online, on the quickly moving online with this course, which is normally given in class. And so part of what I would normally do in class, I'm doing through these recorded videos so that you can watch them and again. You don't have to worry about, some students like to record classes and all that. So you have that here. We still have we're having a regular Zoom conference. So I need you to connect to the Zoom conference or use the forum to ask questions, to get instructions, to learn more about the assignments and what's expected of you. It's important that you purchase the book and read the chapters in the book that correspond to the lecture that we're doing this week. Start thinking about doing your assignments. We're going to very soon have some of the first assignments that are going to be published. And many students like to wait to the last minute, and that's really not a good strategy. So you want to get started on your assignments as soon as possible. And you want to watch all the other videos, and you want to get in touch with the TA or with me if you have any questions, if there's anything that you need as clarifications. So thank you, and we'll see you next week for the next lecture.